Hello, everyone. So for today's set of notes, we're going to be talking about naming some of the simplest compounds that we're going to be dealing with throughout the rest of the year. And everything we've led up to this point is really helping us to understand how these positive and negative ions are forming because they try to create what's called an ionic bond between the two of them. All right, so just a couple of quick reminders. Ions are atoms that lose or gain negative particles or electrons. And so by giving up an electron and another atom gaining that electron, they find and overlap their orbitals to form what we call an ionic bond, which is really just the origin of that name. It's ions that form a bond together, positively and negatively. And so we're going to refer to all the ones that we start off with as binary, meaning two. So we're looking at a positive element and a negative element combining together so that their electron exchange is essentially equaled out. Okay? So step number one is we're going to be looking at the top of each column, 1A through 8A, where we should have our positive and negative charges written from the last set of notes. And then that particular charge indicates how many of that particular ion is going to be needed to form this complete ionic bond. Okay? So an ionic binary compound is always going to form between a metal and a non-metal ion. Okay, the metals are positively charged, meaning they give up electrons, and the non-metals are negatively charged, meaning they're accepting those electrons. So at this point, we can't really have two positive metal ions bond together because they're both giving up electrons, nobody's taking them. And then two negative nonmetals can't form a bond because they're both accepting electrons and they need one of each in order to form these particular bonds. Okay, so just as a reminder, if we locate oxygen, which is in group 6 on our periodic table, we should see that that is going to form a -2 ion. Okay, so the atom is neutral, but the ion has the charge. And if we find the element barium, which is buried at the bottom of the second group, we look at the top and we notice that that means that that particular metal is going to form an ion with a +2 charge. Right? Continue down the line, potassium is in group 1. So the element K, we're going to say forms a +1 charge. And you may be wondering if it's all right just to write the plus or the minus. Do we actually need the 1? I'm okay if it's just looking at +1 or -1, that you just write the plus sign or the minus sign. You don't always have to draw the 1. Okay? So then an example of that would be the element iodine, which is towards the bottom of our 7th group. And again, we notice that that has the pattern of forming a -1 charge. Okay? All right, so a couple of quick, simple steps. When we are given the compound that's going to form between two elements, just like we did earlier, we want to find their charges. So we want to write the cation. Remember, cation refers to the positive ion with its charge. We want to write the anion, which is the negative ion with the charge. And then we really are just going to do some simple math, what we call least common multiple, to figure out how do we get those positive numbers and those negative numbers to add up to 0. Because we want that electron exchange to always add up to 0. And then we want to write that compound in the lowest whole number ratio. You'll see an example of that as we go forward. All right, so if we start with lithium and bromine, we've got the lithium ion, which is a +1 charge because it's located at the top of group 1. And then bromine, which is a -1 charge. So if we have a +1 and a -1, the simplest ratio for those charges to equal 0 is to have one of each ion. So when we write the name or the formula for this compound, we're just going to say LiBr. Okay, so no numbers after each element symbol, 1 lithium ion, 1 bromine ion. We'll see it change up a little bit when we look at the compound that forms between a potassium and an oxygen ion, because potassium's +1 charge is now trying to bond with oxygen's -2 charge. And so for this one, we would need 2 +1s, 2 potassium ions to add up to a total of +2 to counteract oxygen's -2 And so to indicate that we need multiple potassium ions, we put a subscript after the element that we need multiple ions of. Okay, so we see this in the form of K2O. Just like in the formula for water, it's H2O. That means you have 2 hydrogen atoms and 1 oxygen atom. This is very similar in formula to that, where it is K2O. So things get slightly more complicated, although not by much, when you see a formula that's arranged between aluminum and sulfur. So in this instance, we have aluminum, which is only a +3 charge, and sulfur, which is always a -2 charge. And again, the goal is to get the positive value and the negative value to add up to 0. And so with the aluminum ions, we can really only think in terms of multiples of 3. +3, +6, +9. And the sulfurs, we can only think in terms of multiples of 2s, -2, -4, -6. So our least common multiple in this particular instance is only going to require 2 aluminum ions, but 3 sulfur ions. So we have to get our aluminums to add up to +6 and our sulfurs to add up to -6. And we're going to do that by giving ourselves a 2 after the aluminum and then a 3 after the sulfur. Again, those subscripts indicating how many ions in the formula, and then that is essentially multiplying by the charge. So we've got 2 + 3s and 3 - 2s, all equaling 0. Okay? So you probably notice a little bit of a pattern that the positive charge in the metal corresponds to the subscript on the nonmetal. Okay, so aluminum was +3 and we had 3 sulfurs, and oxygen was -2 and we had 2 potassiums, right? That works most of the time, but not all of the time, right? So in this last example where we've got calcium, which is a +2, and oxygen, which is a -2, the first instinct for a lot of my students is that we need 2 of them because we're thinking in terms of the +2 charge. But in actuality, we really only need 1 +2 calcium ion and 1 -2 oxygen ion. So again, thinking in terms of this lowest whole number ratio, we really only need a calcium and an oxygen, 1 of each, because +2 and -2 by itself adds up to 0. So this formula, although it looks very similar to lithium bromide, really has a little bit different of a story going on because it's a combination of a +2 -2 as opposed to a +1 -1. Okay. So when we're given the name of a compound, we want to identify their respective charges and then add them up when we're developing the formula, like we did with these first 4 examples. Okay. If we're given the combination of the elements or given the formula of a particular ionic compound, we also have to be able to derive a name. And so there's a certain system when it comes to naming ionic compounds, and it's pretty straightforward, right? So what we want to do is name the cation, which is our metal ion, in full. Okay, so the metals never really get their names shortened, right? But there's a certain suffix that we apply to the last element, to the non-metal in these compounds, and that's IDE, the "ide" suffix. And that's kind of like when you put the period at the end of a sentence, it indicates finality. It lets us know that we've reached the end of the name for our compound. Okay, so when it comes to naming a binary ionic compound, and we're combining the formulas between barium and fluorine. Okay, so again, barium's +2, fluorine's -1. So the formula is BaF2, but the name for that BaF2 formula we're going to call barium fluoride. Okay, so we don't say barium fluorine, because that just sounds like we just took the element names and slammed them together. But by saying barium fluoride, we're saying there's no other elements connected to the end of this particular formula. So for another example, if we've got aluminum +3, nitrogen -3, we should see that that means that the formula for this compound is just 1 aluminum and 1 nitrogen. But the name for that particular compound, again, we write the full name for the metal, aluminum. And then we want to add "ide" to the end of the name for nitrogen. So we're going to call this nitride. Okay. Now would not be a bad idea for you to pause the video and maybe practice the last two. Otherwise, we're just going to continue on ahead. But if you want to pause it and try these out, you do. Always a good idea. All right, so if we look at sodium, we've got a +1 ion. We look at phosphorus, we've got a -3 ion. So that formula, again, to get those charges to add up to 0, we need 3 + 1 sodiums and 1 - 3 phosphorus ion. And then the name for this compound is, again, the full name for our metal, sodium. And then the "ide" ending off of phosphorus, which is phos-5. Lastly, we've got potassium, which is again +1, and arsenic, which is located under phosphorus in group 5. So that's again a -3. So the formula for this would be similar to sodium phosphide, K3AS. Right? And then the name for this compound, we're going to write the full name for the first element, our metal, potassium. And then we're going to add "ide" to the end of arsenic. So we're going to say arsenide. So that's it for naming binary ionic compounds. We do want to make sure and practice these pretty regularly. These are the standard rules. This is like the base level rules that we need to know how to apply. And the next set of videos are going to be the little details, incorporating more of the elements and more of the specifics to some more unique naming rules.